Here is an example conducted with RCBD, the gradient of wheat variety HAR 6085 with 6 different rates of seeding rate laid out by RCBD design with 4 applications. Here are the replications and here are the treatments. And treatment 1 was 25 kg per hectare of seed rate of this variety, and the other one 50 kg of seed rate per hectare, 75 up to 150 kg of seed rate per hectare. So the treatments were this one. So we have 1, 2, 3, 4, 5, and 6 treatments or 6 levels of seed rates. And each of the treatments were replicated 5 times, 1, 2, 3, 4 times for each and every treatment was replicated 4 times. So the data was this one. So this data or these values were the gradient of the variety by using different seed rates and in different replications or 4 replications. Therefore, as we have seen that the first step of ANOVA is just we have to group the data by treatment. We have grouped by treatment and replication and calculate the grand totals, the treatment totals and replication totals. We have the data here in the treatments here also, and the treatment total is calculated as the horizontal and these values. This one treatment 1 treatment total, and treatment 2 total, treatment 3 total, treatment 4 total, treatment 5 total, treatment 6 total. Whereas here is also the value of replication 1 total, replication 2 total, replication 3 total, and replication 4 total. Just you can sum up this value or this value, and finally you get the grand total here, and also the grand mean is here. And to find the grand total, just we have to sum up all observations, or also just sum up these values, or also sum up these values independently, and we will have similar values. If you need also the grand mean, just you have to divide this value of the grand total by total number of observations. In such case, 16 treatments by 4 replications, we have 24 observations, and if you divide this value by 24, just you have this much grand mean. So the total degree of freedom is this much treatments by this much replications minus 1. We'll have also 23 total degree of freedom. Replication for minus 1, 3 treatments, 6 treatments, minus 1, 5 treatment degree of freedom, and error degree of freedom is t minus 1 in 2 and 4 minus 1. That means 16 r minus 1, and we will have also 15 error degree of freedom. The second step calculates the correction factor CF, squaring the grand square the grand value, and by dividing by number of replication times treatment, and we will have also this much value. The third step is calculating all the sum square values, total SS. Here also total SS is calculated as squaring all observations. That means 51, 13 meaning 51, 13, then this one, next, and up to this one. All these values will be squared and summed up, and then subtracted correction factor to get sum square value, total sum square value. Yes, after we have squared and summed these all observations and subtracted correction factor, we will have also this much total sum square values. And the next step is calculating replication sum square values. In case of replication sum square values, just we have to square all replication totals. That means replication totals are this one, replication 1 total, replication total, and replication 3 total, and replication 4 total, and square all each each replication totals and sum their squares and also divide by treatments. That means the treatments and subtract correction factor will have also this much value of replication sum square. 31 to 75 is the first replication total, the second replication total, this one is the fourth replication total. Divide by the number of treatments, we have 6 treatments and subtract correction factor, will get also this much replication sum square. And then the next step is estimating treatment sum square value in a similar fashion, and we get this much. The difference is in case of treatment sum square values, just we have to square the treatment totals and divide by replications. In case here replications are denominators. In case of treatment, positively. In case of replication, treatments were denominators. In case of replication, so we can use opposite denominators. That means in case of replication, we use treatment as a denominator. In case of treatment, we use replication as a denominator. Finally, after we have calculated or estimating those values, sum square values, just it's better to go here and says from total sum square, just we have subtract the replication and the treatment sum square values, and we get this much of RSS, and then calculate the total. The all mean square values. Sorry, because of influenza, just my sound is not as such attractive, but it's an educational issue. Please tolerate me in such a way. So to estimate the treatment mean square, just we have to divide the treatment sum square by its degree of freedom or treatment degree of freedom, and we get this much value. We have 6 treatments and 6 minus 1, 5 degree of freedom. Then if we divide this one by this one, we will have this one. Similarly, by dividing each value, we will have also this much value. And the next step is calculate the F calculated and tabulated. For treatment mean square, treatment F calculated is equals to treatment mean square over error mean square. And this is what treatment mean square is 3966 divided by error mean square. Error mean square is 120 110 558 555. Sorry, it can be corrected, but it doesn't have significant difference anyways. So F calculated for treatments could be 2.17, and the tabular value at 5 treatment degree of freedom and 15 error degree of freedom. Just we can read from the F distribution appendix table at 5 and 1 level of significance, and we get the value 2.9 and 4.56. We can check this one. Just remember the treatment degree of freedom is 5 and error degree of freedom is 15. By using those two values, calculate the appendix table. So the appendix table 5 treatment degree of freedom. Case of 5% level of significance, we have 5 treatment degree of freedom, 1, 2, 3, 5, and 15 error degree of freedom, 5, 15 error degree of freedom, and 5, 1, 2, 3, 4, 5 treatment degree of freedom. The intersecting point and the value is this one, 2.9 at 5%. Look, 2.90 at 1%, at 5%, sorry, 2.9, yeah, at 5%, and also at 1%. Goes another table that's at 1 F distribution, at 1% F distribution. Similarly, 15 versus 5, 15 in a degree of freedom, and 5 treatment degree of freedom, 1, 2, 3, 4, 5 pieces. In this direction, there are 5 treatment degree of freedom. F is 1, and also here it is the degree of freedom, and the intersecting point is 1, and the value is 4.56. Therefore, we can change this one, 4.56. They are similar. So the values are similar, and also we can read as in such a way that since the efficacy is less than the tabular values, the experiment failed to show any difference among the 6 treatments. The F calculator for replication, replication mean square divided by error mean square. Replication mean square was 648,120 divided by 110,555, and it will give us the value of 5.86 if calculated for replication, and which is greater than that of, because 3.29 and 5.42 at 5 and 1% level of significance in the distribution. Just you can read by using replication degree of freedom. Replication degree of freedom is, we have four replications, and the degree of freedom is 3, but the error degree of freedom is similar to that of the treatment. So therefore 3 and 15, 3 versus 15, and you can use or you can obtain the F distribution values at such case. And then we have to do the relative efficiency of the experimental design over CRD. In order to do this, just we have to use such formula and substitute all the values for the replication. And replication, this is the block mean square value. The block mean square values, you can see that this value, block mean square value, block or replication mean square value is this one. So similar value, similarly, and plus 4 replication and into treatment 6 minus 1. Similarly, this one, error mean square, error mean square, error mean square. This is 5. Do not confuse. Then the relative efficiency is this one. But in case of RCBD, if the error degree of freedom is less than 20, just we need to do adjustment factor or estimate adjustment factor, that's K. Therefore, because of this, we have to calculate this one, and the calculated value is 0.98. This is simply substituting the treatment and the replication in the formula here, and then calculate the value, and we will have also this much K adjustment factor, and multiply the relative efficiency, this one, by the adjustment factor by this, because the error degree of freedom in case of RCBD was less than 20, and then the product value of 1.63 and 0.98 could be 1.60, and this indicates that the use of RCBD instead of RCRD increased the experiment's precision by 60%. So RCBD was efficient, or using blocking design was efficient 60% over CRD. So this it tells the extent how much RCBD was efficient in reducing the experimental error and increasing the precision by this much percent over CRD. And when we submit or input or enter all the values calculated above here, here are the data that we have generated or estimated, and here are also degree of freedoms and some square values and the square values calculated and they have calculated also for the block 5.86 and for treatment 2.17, which was non-significant, designated as NS, and the block was highly significant. That is why we did a relative efficiency. If the block, the calculated block value was less than that of 5%, we couldn't conduct or did a relative efficiency. If this indicates the presence of significant difference, just we need to go see the efficiency or the extent of efficiency, the extent of efficiency using the design over CRD, that means. Therefore, this value is higher than that of this one. That's why two asterisks are placed here, and it indicates that there was a significant difference between blocks. It tells us, whereas there was no significant difference between the 6 treatments. The 6 treatments, or the treatments were also the 6 treatments. The treatments were, we can see here, there are 6 HR with variants, and the yield of there were no significant difference of grain yield of the 6 variants. That means the result tells us this one, and the CV is 6.78. In such case, it's for variety trial, it's tolerable to 0 up to 8%. Therefore, the CV value is better, and it indicates that higher precision of the experiment, even though there is no significant difference between the treatments. So, from this table, what conclusions we may generate in general? The first is there were no significant difference between 6 treatments. That means the seed rate of blade width for grain yield of the variety HR60 85, and the second one is since the experiment failed to show any difference for grain yield among the 6 treatments, even though there are 6 treatments or six varieties, but all of the treatments relatively show similar grain yield, or there was no significant difference between the yield or the grain yield of the varieties. And the other is using the block RCBD was efficient in controlling experimental level by 60% over CRD. That means using block was efficient over CRD. And the null hypothesis could be accepted because the null hypothesis states that there is no significant difference treatments. So the result is in line with this. There is no significant difference. That's why null hypothesis is accepted, and why the alternative hypothesis could be rejected. Sorry. And the precision of the experiment were higher because of the CV in percent is lower, or it's equivalent to 6.8, and this is lower than that of the rule of Gomez and Gomez when in case of the variety trials, the CV value is tolerable from 0.0 up to 8%. So this principle is accepted, and the precision of the experiment based on this experiment, the precision of the experiment is higher